Okay, hi. We are doing what are we doing? Problem 5, I think. Yeah, problem 5. And probably should have prepped the drawing before, but let's go. Um I really should have prepped the drawing. Okay, I'm gonna come back with a drawing. Okay, I drew it at the linked list. So our problem number 5, as you can see, is find the nth node from the end. The entire so given a linked list, the task is find the nth node from the end. And the first, I think, reaction is like, okay, I'm gonna need my concern is time complexity. So I'm like, well, because it's a linked list, we have to traverse through the end if we need the end for sure. So it's gonna take at least one iteration through. And I thought about using multiple pointers because we used that in the last problem, and it's been very useful for numerous problems in the past. But um, I didn't see a way how like it it couldn't it this fast and slow pointer would meet. I know that the situation would be much better remedied with two pointers. I knew that for sure. I just wasn't sure of the actual process of like, okay, well, how do I get the end for I haven't thought it out, and I didn't give myself enough time to be honest. I only had last night and then this morning, which was hectic. So I honestly can't sitting on the bathroom and kind of trying to think of a solution. um but yeah, my first thought was, well, we have to iterate to the end and like um you can find the end and then find the nth node from the end. And the trick, and we could do it, but it would be probably really slow because we could do it in multiple iterations, but it would be slow and we would need to make up for special edge cases, like if there was like one node, or if there was no node, or the linked list was empty and all that stuff. So yeah, so I'm just gonna go with the fast pointer and slow pointer way. And the trick to that is quite clever and really simple. So we start P, not P, we start the slow pointer and the fast pointer. So let me write. So here's the head. Okay. Um, and the head has the slow pointer and the fast pointer to it. And we're kind of starting out in the same position, but we are going to move the fast pointer by n minus 1 positions. Oh, I didn't even say what n was. So let's say hypothetically for this example, n is 3. Let's just say that the n is 3. So the third from the end, so 1, 2, 3. So it would be 5. Yeah. So um, yeah, so this would be the end. So we're gonna move f forward n minus 1 because unlike array linked to start at 1, so we are at 1, so we minus 1 because we want to get to 5. So n minus 1 is so it goes by I don't know if placing matters, 2, 3, 4. Yeah, so 4. And um, then when we get the f, the fast pointer to 5, so I'm gonna erase it if it allows me to. I'm going to erase it and then I'm gonna draw. Okay, well, this is where kind of the fast ended up. Um, and let me just um, write the code for this thingy. So nth from the end, the nth from end, And we have the what's it called, the head and n head node of the linked list as the what's it called, n, and then we're going to go, okay, well, first, and sorry, first, not first, fast, and slow is equal to head and head. So they're both initialized of the same node, like I said, and then we're going to, we have to, I guess, and then we have to write a count. So count currently is at 1, like we said, because it's a linked list, and then while, so we're gonna write a while loop. So while count, maybe I should shorten, count is less or equal to n minus 1. I don't, is there supposed to be a parentheses right here? Doesn't matter. So it's saying we're going to increment, well, we haven't said it yet, but we are going to get f to the point. So for every, oh gosh, how do I know? For every, we're going to get the fast pointer to fast.next until the n minus 1 of that point. And then we're going to increment count by 1. Yeah, and that's how we got here. And now we're just, now it's really clever. So now and this is the solution. So our goal is to find this and return it or print it or something. So that means that and if I think I was supposed to do like a, oh, if there's no if there's no head or there's no just edge cases, I was supposed to take care of that, but I think I forgot. Where do I write it? So we have to do an edge case, which I just remembered. So if it's like a node, or if it's a linked list with like what's it called, 2 or less, we have to account for that. So in that logic, it's like we have to go if, oops, I don't know how I got to yellow. So we have to write like if, oops, so then we're going to return fast.next because it has to be one of them. So yeah, that covers that case. And then the last thing is we have to do a while loop and go, okay, well, if there, while the fast.next is true, so while there is a fast.next, we just gotta move each pointer forward by 1. So slow.next, which means that Just trying to think of more edge cases because that's something I haven't thought about, and it's taking me some time to process it. Give me a second. I'm going to consult my notes because I wrote I think I wrote some common edge cases down in some of my general notes. So blah, 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 blah. Okay, so if the data is empty, okay, if the value can't be found, or if items both like, oh, if both the items being swapped is the same, but not swapping, we're just trying to find the nth node, so that should be okay. Okay, well, yeah, okay, it should be okay. So yeah, we're just going to move after fast gets to n, then we are going to so still at 1 and fast is at now way ahead by n. So now we're just going to increment each one of them by 1 y until fast gets to until fast gets to the end, or it gets to null, and or fast dot next gets to null. So once fast dot next gets to null, it will break out of this while loop because it will become invalid, and then we are going to just return. Yeah, we're just going to return the slow pointer because it would have inevitably ended up where fast currently is, like at 5, or the something from the end. Yeah, you know, the logic works. I suck at explaining. Oh my god. So we're just gonna return s, or the slow pointer, because the slow pointer will eventually end up here. So let's try this out. So we're going to, god, I don't know how to draw this. So we're going to move fast by 1, slow by 1, fast by another 1, and slow by this one, and then fast will be here, and slow will be here. Oh, slow dot next, sorry. Yes, but yes. So we're going to return slow, and I'll have a pointer pointing at 5, which is where fast was originally. And yeah, and we remove by 3. I try to think about, like, if the array was, or the linked list was like a lot longer, that would work, and all that stuff. Yeah, I mean, it's like, because we skipped whatever forward, a fast forward, so like, so we'll catch up once fast whatever is the end, because we just have to. Yeah, anyways, it works. It magically just works. I checked this on Meet. But yeah, I was just kind of thinking, like, picturing in my mind with the numbers blown up, and I'm just like, what is this magic? I don't. So yeah, I don't think I did a great job explaining, but it was a hell of a lot easier to draw than number 3, and this wasn't that easy to draw because I don't. It's confusing. So time and complexity is this. I don't know if I discussed it. I don't remember, but it's linear time because we have to traverse through it once, and the length depends on what the where the length of the linked list is. So yeah, and uh, 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 space complexity. Well, it's a linked list, but we didn't have to create excess structures or anything since we're using 2 pointers. The space complexity is constant. If we made a hash table, then it would be, I believe, O of m time, because we're creating a hash table the size of m, but we're not using a hash table, so I think that's it. I don't know. I don't actually know the, like, intricacies of the other solution. I know the brute force solution, which is still a constant time. But then the brute force way, where there's scanning, multiple scans, is n square for time complexity. So I don't know. Okay, anyways, that's it. That's number 5. Cool. Bye.